The promise of electric vehicles has always been presented as a clean break with the past, a definitive solution to the environmental and energy problems of the automotive sector. However, behind this optimistic narrative lies a component that concentrates both the hopes and the fragilities of this transition: the battery. More specifically, the lithium-ion battery, which has become the technological heart of the modern electric car, but also its biggest point of tension. Everything revolves around it, from performance to range, from price to safety, creating an almost absolute dependence on a chemistry that was never designed to sustain a global revolution of this scale. From a structural point of view, lithium-ion batteries carry limitations that go far beyond simple engineering challenges. They require complex electronic control systems, constant temperature monitoring, active cooling, and multiple layers of protection against failures. Each of these solutions adds cost, weight, and potential points of failure. The result is a highly sophisticated yet fragile system where small operational deviations can have serious consequences. Instead of simplifying the automobile, the battery ends up transforming the electric vehicle into an excessively sensitive machine. Cost is another critical factor hindering mass adoption. Even after years of industrial optimization, lithium-ion batteries continue to represent a significant portion of the final vehicle price. This is not only due to the material itself, but also to all the infrastructure needed to make it minimally safe and reliable. Furthermore, the dependence on elements such as lithium, cobalt, and nickel creates a vulnerable supply chain, subject to geopolitical instability, price fluctuations, and the risk of shortages. Electrification, which should liberate the automotive sector, ends up trapped in new strategic dependencies. There is also a less discussed but extremely powerful factor: consumer fear. Spontaneous fires, accelerated degradation, loss of autonomy over time, and high replacement costs fuel a perception of constant risk. Even when statistically rare, these events gain enormous prominence and erode public confidence. For many buyers, the battery ceases to be just a technical component and becomes a source of anxiety. The promise of an electric future directly conflicts with the sense of insecurity that current chemistry conveys. At the heart of this contradiction lies a fundamental paradox. The battery is presented as the solution that makes the electric car viable, but at the same time it is the main obstacle to its definitive popularization. While the industry insists on extracting more performance from a technology that already operates close to its physical and chemical limits, the promise of electrification remains threatened. The lithium-ion paradigm, which propelled the first phase of this revolution, is beginning to show clear signs of exhaustion, raising an inevitable question: what if the problem was never the implementation, but rather the choice of chemistry from the beginning? At certain points in industrial history, evolution ceases to be sufficient. Small improvements, marginal adjustments, and gradual optimizations are no longer able to address the structural limitations of a technology. It is at this point that decisions emerge that seem risky at first glance, but which, when understood in depth, reveal a powerful strategic logic. Tesla's choice to abandon lithium does not fit the traditional model of incremental innovation. It signals a conscious break with the dominant path followed by virtually the entire automotive industry. By opting for an aluminum-ion battery, Tesla is not simply swapping one material for another, but questioning the very foundation upon which electrification has been built in recent decades. This is a decision that involves engineering, economics, logistics, and even industrial philosophy. Instead of insisting on complex, expensive, and unstable chemistry, the company proposes a new technological axis based on simplicity, abundance, and predictability. This change does not seek to impress with isolated numbers, but to redefine what it means to make electric cars viable on a global scale. This strategy reveals a long-term vision that goes beyond product cycles or immediate competitive advantages. Aluminum-ion is not presented as a temporary solution, but as the basis of a new energy architecture for the next generation of vehicles. By doing so, Tesla anticipates future bottlenecks that would inevitably arise with the massive expansion of lithium-ion electric vehicles. Instead of reacting to supply crises or abrupt cost increases, the company is redesigning the system before it collapses. There is also a profound industrial element to this choice. Aluminum is a widely mastered material with mature processes, consolidated supply chains, and a global presence. By aligning the battery with a raw material already integrated into heavy industry, Tesla reduces risks and gains control over critical variables. This approach contrasts with the growing reliance on rare minerals and politically sensitive regions, which have made electrification vulnerable to external factors that are difficult to predict or control. Ultimately, this disruption represents a shift in mindset. Instead of asking how to extract more performance from a limited technology, Tesla is questioning whether that technology still makes sense. The bet on aluminum-ion technology suggests that the future of electric vehicles will not be defined solely by range or acceleration, but by the ability to build robust, scalable, and economically sustainable systems. It's a quiet yet profound turning point that redefines the course of electrification from its very foundations. One of the strongest pillars of the transition to aluminum-ion technology lies in the very nature of the chosen material. Unlike lithium, cobalt, or nickel, aluminum is one of the most abundant elements in the Earth's crust. This abundance is not merely a geological fact, but a determining factor for the economic stability of any technology that depends on it on a large scale. When the raw material is widely available and globally distributed, the risks of artificial scarcity and speculation decrease drastically, creating a more predictable environment for industry. The aluminum supply chain is already mature, robust, and widely integrated with the transportation, construction, and heavy manufacturing sectors. This means that much of the infrastructure needed for its extraction, refining, and processing already exists and has been operating on a global scale for decades. Unlike emerging lithium supply chains, which still face logistical bottlenecks and depend on intensive investment, aluminum offers an industrial base ready to be expanded without abrupt disruptions. This maturity reduces costs, lead times, and uncertainties. From a geopolitical standpoint, this choice also represents a significant reduction in systemic risk. Lithium and other critical metals are concentrated in a few regions of the planet, often subject to political instability or strategic disputes. Aluminum, on the other hand, is produced in dozens of countries, diluting the power of control and making the system less vulnerable to external shocks. For an industry seeking to electrify hundreds of millions of vehicles, this decentralization is not a detail, but an essential condition. Price predictability is another key element in this equation. While the rare minerals market suffers violent fluctuations, driven by speculation and abrupt changes in demand, aluminum presents a much more stable historical curve. This stability allows for long-term planning, safer industrial contracts, and, most importantly, a reduction in the final cost for the consumer. When the main component of a vehicle ceases to be a financial unknown, the entire price structure becomes more accessible. Ultimately, the choice of aluminum redefines the concept of cost in electric cars. It's not just about making a component cheaper, but about transforming the battery into a predictable, industrially reliable, and economically sustainable element. This change creates the necessary conditions for electrification to cease being a niche product and, for the first time, approach truly widespread adoption. Excessive complexity has always been one of the greatest enemies of reliability in technological systems. In the case of lithium-ion batteries, this complexity manifests itself in layer upon layer of solutions created to compensate for fundamental chemical limitations. Redundant sensors, sophisticated protection circuits, continuous monitoring software, and active cooling systems are necessary not to improve the user experience, but to prevent failures. The system works, but only as long as everything operates within extremely narrow margins. The aluminum-ion battery proposes a different logic, based on tolerance rather than obsessive control. Its chemistry allows it to operate with a greater safety margin, reducing the need for constant monitoring of each cell. This translates directly into fewer sensors, fewer auxiliary circuits, and a simpler electronic architecture. When the system accepts variations without collapsing, the engineering ceases to be defensive and becomes structurally robust. This simplification has a ripple effect throughout the vehicle. Fewer components mean fewer potential points of failure, less need for maintenance, and a lower probability of unexpected defects. Each element removed from the system is not just a cost saving, but a real reduction in risk. Instead of adding solutions to known problems, the aluminum-ion approach eliminates the problem at its source, making the assembly more resilient to everyday use. From an industrial standpoint, this robustness also facilitates large-scale production. Simple systems are easier to assemble, test, and standardize. Variability between units decreases. Quality control becomes more efficient, and operating costs fall. This predictability is crucial when the goal is not to produce thousands, but millions of vehicles per year, while maintaining high reliability standards. Ultimately, the equation is straightforward and powerful. Less complexity results in fewer failures, lower hidden costs, and greater confidence in the final product. By replacing engineering based on trade-offs with one based on tolerance, the aluminum-ion battery redefines what robustness means in the context of electric vehicles, finally bringing them closer to the functional simplicity that has always characterized the most successful automobiles in history. Temperature has always been the silent enemy of modern batteries. In the case of lithium-ion batteries, excessive heat is not just an inconvenience, but a direct threat to the integrity of the system. Small temperature increases can trigger chain reactions, requiring complex and heavy cooling mechanisms to keep everything under control. This thermal fragility makes heat management one of the most critical, expensive, and bulky elements of the entire electric vehicle. The aluminum-ion battery completely breaks with this logic. Its chemistry exhibits a drastically superior thermal tolerance, capable of operating stably at temperatures that would reach catastrophic levels for lithium. Instead of collapsing under high heat, the system maintains its structural integrity, reducing the risk of serious failures. Temperature ceases to be a rigid limit and becomes just another operational variable. This thermal resistance redefines the need for cooling systems. Dedicated radiators, complex liquid circuits, and additional components become unnecessary or significantly reduced. The impact of this goes beyond saving on parts. Fewer cooling systems mean less weight, less energy consumption, and less space occupied inside the vehicle. It's a simplification that reverberates throughout the automotive architecture. From a safety standpoint, the difference is even more profound. The risk of uncontrolled overheating, one of the main concerns associated with current batteries, is drastically mitigated. The thermal stability of aluminum-ion transforms extreme scenarios into manageable situations, eliminating the need for emergency solutions. The system stops operating at its limit and starts working with a wide safety margin. In the overall context, this thermal revolution is not just a technical advancement, but a psychological shift. When heat ceases to be a constant threat, the entire perception of the reliability of electric cars is transformed. The battery stops being a fragile component that needs to be protected at all costs and becomes a solid structure, capable of withstanding the real world without excessive compromises. When bulky and complex systems become unnecessary, design ceases to be a concession and becomes a creative choice again. The elimination of large cooling structures and redundant protective layers opens up space for new freedom in the architecture of electric vehicles. The aluminum-ion battery not only occupies less functional space, but also imposes fewer restrictions on how the car is designed from the outset. This change allows for a more balanced mass distribution, directly benefiting vehicle dynamics. With less weight concentrated in auxiliary systems, engineers gain flexibility to position components more efficiently. The result is a more stable, agile, and energy-efficient vehicle. The architecture ceases to be a compromise between safety and performance and begins to integrate both naturally. The impact on interior space is equally significant. The reduction of peripheral components frees up areas that were previously inaccessible, allowing for more spacious cabins, lower floors, and better use of the vehicle's total volume. This translates into greater comfort for occupants and greater versatility in everyday use. The electric car ceases to look like an adapted vehicle and is designed as electric from its very essence. Modularity also benefits from this structural simplicity. With fewer dependencies between systems, it becomes possible to develop more flexible platforms capable of accommodating different sizes, styles, and purposes. The same battery concept can support everything from compact urban vehicles to larger models, without requiring extensive redesigns. This standardization accelerates development and reduces costs across the entire product line. Ultimately, this design freedom represents technological maturity. The car finally stops revolving around the battery as a problem to be overcome. Instead, energy becomes invisibly integrated into the vehicle, allowing form, function, and efficiency to work together. It is at this point that the electric car ceases to be a technological exception and becomes, in fact, a new standard. For years, the battery was treated as an almost untouchable component, a sealed block that could only be accessed in extreme situations and at high cost. This perception created a distance between the user and the vehicle's energy heart. Any problem, real or potential, was associated with long repair periods and unpredictable expenses. The battery, instead of empowering the driver, became an element of apprehension. Aluminum-ion-based architecture allows for a completely different approach. With greater chemical stability and less dependence on critical systems, the battery can be organized into independent modules. These modules can be replaced, inspected, or upgraded in isolation without the need to disassemble the entire assembly. Maintenance ceases to be an invasive intervention and becomes an objective technical procedure. This modularity drastically reduces repair time. Instead of immobilizing the vehicle for days or weeks, replacing a specific module can be done in much shorter periods. For the user, this means fewer disruptions to their routine and greater cost predictability. The workshop ceases to be a place of uncertainty and begins to operate with clear and standardized processes. From an economic standpoint, the impact is immediate. Repairing only what is necessary costs less than replacing entire systems. This logic brings battery maintenance closer to what consumers already know about other automotive components. The idea that the battery is a disposable and excessively expensive element is beginning to lose strength, giving way to a more rational and accessible relationship. Ultimately, this change redefines the electric vehicle ownership experience. The battery ceases to be a technical mystery reserved for specialists and becomes an understandable, repairable component integrated into the car's life cycle. This proximity generates trust, reduces psychological barriers, and brings the electric vehicle closer to the everyday reality of the average consumer. Durability has always been one of the most sensitive points in the debate about electric vehicles. The idea that batteries degrade rapidly and lose value over time has created a persistent fear, especially in the used car market. With lithium-ion batteries, this concern is not unfounded, since chemical degradation is an inevitable process, accelerated by intense charging cycles, heat, and the natural aging of the material. The aluminum-ion battery profoundly changes this equation. Its chemistry exhibits much greater resistance to degradation over cycles, allowing for thousands of charges with minimal capacity loss. In practical terms, this means a lifespan that can exceed decades of normal use. The vehicle ceases to be seen as a fast-moving consumer product and begins to be perceived as a long-term asset. This longevity changes market behavior. An electric car with a durable battery maintains its value for much longer, reducing depreciation and strengthening the resale market. The fear of buying a used electric vehicle begins to disappear when the battery ceases to be a risk factor. This creates a virtuous cycle in which more consumers feel safe to embrace electrification. From the user's point of view, the emotional relationship with the vehicle also transforms. Obsolescence ceases to be a constant threat, and ownership takes on a new meaning. The car is no longer something that needs to be replaced quickly to avoid financial losses. It begins to accompany the owner for long periods, with predictable performance and controlled costs. In a broader context, this extreme durability redefines the very concept of sustainability. A product that lasts longer consumes fewer resources over time, regardless of its initial efficiency. By radically extending battery life, aluminum-ion not only solves a technical problem but transforms the electric car into a solution truly aligned with a long-term vision. Far beyond performance figures and technical specifications, the adoption of a new technology depends on something more subtle and powerful: trust. In the case of electric vehicles, the fear of fires and catastrophic failures has become a significant emotional obstacle. Even when these events are rare, their impact is enough to generate lasting insecurity. For many consumers, the fear lies not in the probability, but in the consequence. The chemical stability of the aluminum-ion battery directly influences this perception. By drastically reducing the risk of uncontrolled thermal reactions, the system eliminates one of the main anxiety triggers associated with modern batteries. The vehicle ceases to be seen as a potentially dangerous object and begins to convey a sense of solidity and predictability. This psychological change is as important as any technical advancement. When users trust the system, their behavior changes. They park without worry, charge the vehicle without fear, and use the car more naturally in their daily lives. The technology ceases to be something that requires constant vigilance and begins to operate in the background. This normalization is essential for the electric car to be perceived not as a risky innovation, but as a mature alternative. From a communication standpoint, This perceived safety also reduces the need for complex justifications and explanations. The product begins to sell itself on its peace of mind, not just on performance promises. The absence of fear becomes a silent, yet extremely effective argument. The consumer doesn't need to understand the chemistry to feel that it is reliable. Ultimately, trust isn't built solely through testing and certifications, but by eliminating visible risks. By offering a battery that inspires confidence from the very first contact, aluminum-ion technology removes one of the deepest emotional barriers to electrification. It is at this point that the technology stops being convincing and simply becomes accepted. When discussing sustainability, the debate often focuses solely on the moment the vehicle is in use. Zero emissions from the exhaust become the main argument, while the entire product lifecycle remains in the background. However, the real environmental impact of a technology begins long before it reaches the streets and continues long after its useful life. It is within this broader horizon that the aluminum-ion battery reveals a structural difference. Reducing dependence on intensive mining is one of the central points of this change. The extraction of lithium, cobalt, and nickel involves complex processes, high water consumption, and significant impacts on sensitive ecosystems. Aluminum, on the other hand, already has an established supply chain, with widely disseminated extraction and recycling techniques. This does not eliminate the environmental impact, but it makes it more controllable and predictable. Battery longevity also plays a decisive role. A system that lasts for decades drastically reduces the need for continuous production of new units. Less production means less extraction, less transport, and less disposal over time. Sustainability ceases to be a discourse based on momentary efficiency and begins to rely on durability as a central principle. Another relevant factor is the recyclability of aluminum. Unlike materials that lose properties when reused, aluminum can be recycled repeatedly with relatively low energy consumption. This creates a more closed loop in which the material maintains value throughout its entire life cycle. The battery ceases to be an environmental liability and becomes a reusable resource. Overall, this approach redefines what sustainability means in the automotive sector. It's not just about reducing direct emissions, but about rethinking the entire production structure that supports the electric vehicle. By aligning durability, abundance, and recyclability, the aluminum-ion battery points towards electrification that is less symbolic and more consistent with real environmental challenges.